Assalamu alaikum. Today we are going to discuss the Maxwell velocity distribution. This velocity distribution is generally applied to the distribution of velocities in a gas. Here we start with the Maxwell distribution function that is given by this relation. If you remember, this Nj represents the energy of particle and the jth energy level of the system, and Gj, this is known as the degeneracy of the energy level, and this represents the number of energy state and that particular energy level. Alpha and beta, you remember, these were the undetermined multiplier we use in the distribution function for the Bose-Einstein, for Fermi-Dirac and Max-Boltzmann. And here we are going to find the value for this beta, and for alpha we will calculate this in the next lecture, which will be about the partition function. And this Ej is the energy of the jth energy level. If we rearrange this equation, Nj is equal to this one, we call it equation number 1. Similarly, we know that n is equal to, n is the total number of particles, is equal to the sum of all the particles in all the energy state. And if we put equation number 1 here in this summation, so we will get this relation, this e power minus alpha, this is independent of j, so we can take it out of the summation sign. So we have this equation number 2. Similarly, the total energy of the system is given by this relation where Nj and Ej, once you multiply this, so this will give us energy of the particle and the gth energy level. And when we sum all the energy of all the particles, so this will give you the total energy of the system. So if we put the value of Nj from equation number 1 over here, so we get this relation. And again, if we take this e power minus alpha out of the summation sign, so we will get this relation. Now keep in mind that all these equations are applicable to the discrete distribution of the energy state. And when we talk about the gas, so there the energies are continuously distributed. So we have to modify these equations so that they could be applicable to the continuous energy distribution. So we have continuous energy distribution in the gases. So we replace this Gj by Ge dE and summation sign by integration. You know that this is the very usual procedure that we when we go from the discrete system to the continuous distribution system, so we replace the summation sign by the integration. And then Ge dE actually is the number of energy states that lies between E and E plus dE. So the equation 1, 2, 3 on the previous slide could be modified like this, that Nj we will be replaced by Ne dE, and Gj will be replaced by Ge dE. So you have Ne dE is actually the number of particles between the energy state E and E plus dE. Similarly, the total number of particles. So here, you see here the sigma sign is replaced by the integration and Gj by Ge dE. Similarly, equation number 3 can be modified like this. According to the kinetic molecular theory, the particles are non-interacting, so their potential energy is 0. And if this is the case, then the total energy is entirely kinetic. That is, E is equal to P square by 2m, where P is the momentum and m is the mass of the particle. So this means that for each different value of energy, there is a corresponding value of momentum. It means that the number of energy state between E and E plus dE is equal to the number of momentum states between P and P plus dP. That is, GE dE is equal to GP dP. Now, volume of the phase space. So the phase space is actually a 6-dimensional space where we have three variable for the space coordinate and three variable for the momentum coordinate. So the volume of the phase space for which the momenta lie between P and P plus dP is given by tau is equal to this relation. So here we have 6 variable, 3 for the space coordinate and 3 for the momentum coordinate. That is why we have 6 integral sign. So we can rearrange this like this. So this one will give you the momentum, the normal momentum and the special coordinate system, and this gives you the momentum of the spherical shell and the phase space. So this is the normal moment volume, is represented by V, and this is the momentum of the spherical shell and the phase space given by 4 pi p square dp. So this is actually this thing, that we have a spherical shell, this blue spherical shell, which have a radius p, and the thickness is dp. So for example, the surface volume, the surface of this inner sphere will be 4 pi p square, and if you multiply by the thickness, so this will give you the volume, and the thickness is dp. So the tau is the volume of the phase space whose momentum lie between P and P plus dP, where this V is the volume in the spatial coordinate system. Now the minimum volume of a cell, that is an energy state in phase space, is calculated by the uncertainty principle. So you know that the uncertainty delta x px, this is h, delta y py, this is h, delta z pz, this is h. So the volume, this represents the volume of the cell. This is the minimum possible volume which correspond to an energy state. This will be equal to h cube. So now you have the volume of the phase space for momenta between P and P plus dP, and you have the volume of the cell or the energy state. So if you divide this by this, so this will give you the total number of energy state. So the total number of energy state in the phase space having momenta between P and P plus dP is given by this equation number 11. This is the total volume, this is the number of each cell. So this gives you actually the number of cells, and the number of cells are actually equal to the number of energy states. So now if you use equation number 11 and equation number 8, so here this is equation number 11 and this is equation number 8. So the number of energy state between E and E plus dE will be equal to this one. Now here on the left side you have the variable E, and on the right side variable P, so you can replace the variable P in terms of E. So P is equal to 2 and P square is equal to 2me, and here dP, so d2me power 1 by 2. If you do simple calculation and rearrangement, so you will arrive at this equation number 12, which gives you the number of energy state lying between E and E plus dE. Now if you use equation number 12 and equation number 5, equation number 5 was this one, equation number 12 was this one, what you need to do, you put this GED is here, so you put this value in place of GED. So if you do this, you are here in this equation. Now you just bring the constant out of this integral sign, so you will write it over here. And if now you have to integrate this integration, and you are here, and this is you can integrate this equation by putting e is equal to x square. You will have d is equal to this one, so this integral, this one will reduce to this one, and this integral is actually a specific form of this general integral for n is equal to 1. So if you put n is equal to 1, so here, so 2n minus 1, so you will have this one 1, okay, this 2 to the power n plus 1, n is equal to 1, so 2 to the power 2, so 4, so you have 4, and in place of beta you have here a, so pi, so this is a to the power n, n is equal to 1, so beta to the power 1, so beta, and pi by a, so there you pi by beta. So if you rearrange, so you will get total number of particles by this equation number 13. Now you can write this equation 13 in terms of e power minus alpha is this one. Now if you use equation number 12 and equation number 14 and equation number 6, equation number 6 was given by this, and 12 by this, and 14 by this, so you are here. So what you do, this is 14, so you put this relation, and this is 12, so you put this, and e power beta es is the same thing. Now you again bring all the constant out of this integral sign and do some simplification, so you will get this relation. Now again you have to solve this integral, and it is given by this, and if you arrange this equation, so you are get equation number 15. And for solving this integral, again you have to do the same thing. So when you is equal to x square, you are there, this relate this, and now you see here, this is for 2n, and here x square n is equal to 2. So you just put n is equal to 2 over here, so you will get this relation, and of course beta is in place of a. Now according to the equipartition principle, energy of the system of n particles is given by this. So if you compare these two relations, so from here you can get beta is equal to 1 by kt. So here we have calculated the value of beta, which is the inverse of Boltzmann constant and absolute temperature. Now if you put equation number 17 and equation number 14, so you will get this relation. So beta 1 by kt. Now you can write equation number 1. So the equation number 1 was this one. So nj, in place of nj you write nede, in place of gj you write gede, and e power minus alpha, e power minus beta is simpler. So now you have a value for e power minus alpha, you have to put the value of e power minus alpha over here. You have the value of beta, so you have to put the value of beta over here, and you also have the value of gede given by this. So if you put all these values, so you will get ned is equal to this one. You just make some simplification. So after the simplification, you will get this relation. So this is the relation for the number of particles in the energy state that lie between E and E plus dE. Now, the number of particles in the momentum state that lie between P and P plus dP is given by this one. So you know that NED is equal to NP dP, and for NED we have this relation on the previous slide. So what you need to do, you just put E for P over here. So E is equal to P square by 2m. Here you have E, so P square by 2m. and here your E says P squared by 2m. So you make some simple calculation over here, and then you just it is you are here, and then you rearrangement and some simplification. So you are here. So equation number 21 represent the number of particles for momentum between P and P and dP. Now you can also write a relation for the number of particles having velocity between V and Vt. So you P, so you look at by V, and here you have P square, so this is mv whole square, you have P square, so mv whole square, this is P mv. So you do some calculation and simplification. So you are here, and for the simplification will give you this relation, and now you can have a relation, the number of particles is a function of velocity. But means that if you count the different velocity, so it means that you are counting the number of particles. So counting velocity means counting the number of particles. Now, and this depends upon two things, velocity and temperature. Actually, if you increase the temperature, so the velocity is of course increasing. Okay, so if you plot this, so you will have this relation NV. So you have this curve. So if you and remember that the area under the curve gives you the total number of particles of the system. If you increase the temperature, so the velocity go on increasing. So here the velocity will go here. If you further increase, the velocity will go here. So with the increase in temperature, the width of the curve increases and the height of the curve decreases in order to remain to keep the number of particles is constant, because with the increase in temperature the number of particles remain the same. So this was all about the distribution of velocity by Maxwell distribution function, and you may have this relation exactly in your highly reasoning book, which you have studied in your semester 4 or 3, I think. So now I have an assignment for you, that what you need to do, you have to find the most probable speed, the average speed, and the root mean square. And these and for these calculations you can take help of highly reasoning book, where you have already calculated this. So for the most probable speed, we written by Vp. So if V is equal to Vp, it means that the Nv is equal to maximum. And if N is Nv is maximum, so it differential with respect to will be equal to 0. So if you do this, so you have Nv over here, you differentiate with respect to dV and put it equal to 0, and represent the velocity by Vp. So after the calculation and simplification, you will get this relation. So this is the most probable velocity in this velocity distribution. Why we call it the most probable velocity? Because the maximum number of particles has this velocity. You see here, this is the velocity associated with this peak. So this peak is actually the maximum number of particles. So the velocity that is associated with the maximum number of particles is known as the most probable velocity. Similarly, the average speed or average velocity is given by this. So this is the velocity of all the particles, and then you divide by the total number of particles. So you know that this summation actually represents integration actually represents the summation. So if you solve this integral, so you will get this relation. Similarly, the root mean square speed is actually the square average root square root of the square average. So what you need to do, you find the square average. So the square average is exactly like this one, but here square, you put it here square. So square average is equal to v square n. So you put it here, and then you solve this integral, especially this integral, and simplify the calculations. You will get this relation. So this was all about the Maxwell velocity distribution and this assignment. You have to submit this assignment in 2 days. You just calculate it and then send it to me through your WhatsApp group. Okay, so the next lecture will be about the it is partition function. Okay, thank you, sir.